So, you want to save the world with clean energy? Make money doing it? Confused about the economic and technical realities of residential and commercial solar, batteries, heat pumps, EVs? Want the real-world scoop on new energy technologies, not manufacture hype? Then tune in to the Weekly Energy Show, hosted by Barry Cinnamon. Insights from Barry's 40-plus years in the solar and energy industry will help you understand the future ways we'll generate and consume energy. And now, here's Barry.
Welcome to this week's Energy Show. Now, when it comes to electricity, it seems like data centers are gobbling up all of our available electrons. They're possibly going to be raising electric rates for everyone, and that's creating a consumer backlash, which isn't obviously good for consumers, isn't good for data centers, and may not even be good for the utilities. But the question is, why do data centers need so much power? So on this week's Energy Show, we'll answer that question and go into some of the details about data centers, some of the jargon that's used, and some of the rationale for why they're designed the way they are designed. All right, so first, simple, what do data centers need all that power for? Well, the answer is every electronic device needs electricity to operate. From your car remote control with that tiny little battery in there, to your desktop computer plugged into the wall, to server farms, to massive data centers. And the electronics get hot as they use more power. They've got capacitors, they've got transformers, they've got wiring, they've got chips that get really, really hot. They need heat sinks. All of that electricity, all of that power is turned into heat. And everything that gets hot needs cooling, otherwise it's going to get too hot to operate. And as you know, electronics generally don't like a lot of heat. The hotter they run, they're often slower. They slow the clock speeds down so they don't get as hot. And they typically have a shorter lifespan. The hotter things get, the less time they last. And the other thing about electronics is there's more resistance in the wires when things get hotter. So that slows things down and actually creates even more heat. So let's kind of just conceptually draw a box around a giant data center building. There's huge amounts of electricity going in, and there's huge amounts of heat being dissipated. You got to get rid of that heat. And the product from a data center is basically just data. And that data goes out in flashes of laser light into slender bundles of fiber optic cables. It's not like we're manufacturing something. It's not like we're converting one form of energy into another. Basically, all that power is being used to do the data crunching and send out those signals over fiber, and everything else is heat. Based on the first law of thermodynamics, virtually 100% of all the power going into the data center turns into heat. The only energy that's leaking out besides heat are tiny bits of laser light and maybe some radio signals. Why are the data centers rated by their power requirements instead of things like chip processing power? When I buy a computer, it'll tell me how fast it's processing, megaflops, whatever it can do, do all this data crunching fast. But the data center building and the facility, it's like, how many megawatts of power do you need? The electricity used by these data centers dictates the limits of the physical infrastructure that the data center can support. So that power availability, how much power you can get to the current or the future building, determines the construction permits you need, how many transformers you need, how many wires you need from the utility. It determines your operating costs, and it determines the cooling capacity. And so you obviously have, and anywhere you're basically saying, hey, I'm going to need a lot more power, there's going to be limitations of the grid as to what can be delivered over the existing wires, or what can be delivered over planned wires to that facility, and what can be delivered from, let's say, nearby or remote power plants that would connect to that facility. You also need to know what the cooling needs, because as we talked about, most of that heat needs to be cooled, otherwise the chips are going to overheat. And then there's new AI technology that's coming out that theoretically is going to allow you to do more AI processing per chip. And that's actually in many ways may require these chips to run even hotter. So speaking of heat, we're going to have to find a way to cool that data center. And the place where that heat is being created is in the actual chips and in the actual servers that are in the data center. And so that's one with air conditioning, because basically most of these data centers aren't being built in Iceland where you can just open up the windows. It's basically in a suburban or urban or more frequently in a rural area where you got to get rid of that heat. So there's two ways to do that cooling in this air conditioning. It's the same two ways that commercial buildings and homes actually do their cooling typically. You can use either evaporative cooling, which a lot of commercials do. They have these cooling towers on the roof of the building. There's these big fans with big pools of water. They have huge heat exchangers in these cooling towers. So they pump the hot refrigerant up there, and then they spray those heat exchangers with water, and that evaporates and that cools the water down. So it's a very efficient way to cool. Now, the other way to do it is what you have at a home air conditioner, where you basically are just blowing ambient air temperature outside. It might be 80 degrees. You're blowing 80-degree air over these heat exchangers, these condensers. And then that 80-degree air takes away the heat from the condensers. And you may be blowing 95-degree heat out. So it's air to air or evaporative cooling. The problem with evaporative cooling is it uses a lot of water. Now, it uses less energy, but it uses a lot of water. And air-to-air cooling, since you're not evaporating water to absorb that heat, uses a lot more power. You can have a data center that's very energy efficient, that's going to be very water inefficient, or you can have a data center that is very water efficient. They're not using a lot of water for evaporative cooling. They're going to use a ton more electricity. Now let's dive into a little bit of the terminology and the jargon that confused me and sometimes still does confuse me about the terminology related to data centers. So first, how is the computing output measured in a data center? Well, we're kind of measuring the facility by megawatts, but the actual computing output is tracked with metrics like teraflops. And a teraflop is 1 trillion floating point operations per second. You know, one trillion divisions, multiplications, yes to no, and NOR gate. All right, now that's computing power. There's now AI task specific metrics, which is something called an inference token per second. So that, kind of looking into this, what's a token, you may ask? Obviously, that's what I asked. A token's a fundamental unit of data processed by language models like ChatGPT, Claude, and Gemini. So rather than kind of reading whole sentences and whole words, AI breaks the text into smaller chunks, maybe 1 or 2 letters at a time, and then it processes data based on that. So that's a token. And then you measure how fast you're able to process those tokens. And a good metric, since we're measuring the data center capacity by megawatts, and the ultimate goal is to find data centers that are going to have a very high degree of performance per watt. We want to squeeze the maximum number of tokens out of every watt of power used. And that's going to give you a data center that's going to have the most capacity. Yeah, now we have to go back and see, what are we doing with all that megawatts of power? How much are we using for cooling? How much for evaporative cooling? What would it be if it were air-to-air cooling? Those are some of the basic concepts. And then kind of looking into this, there's a few different kinds of data centers that are out there in the industry. And I was kind of wondering, what's the difference between these training data centers versus inference data centers? And so basically, an inference data center is optimized for what they call the execution phase of artificial intelligence, where a pre-trained AI model is basically going to apply what they learned to process real-world queries and give you answers. So, for example, what's the average cost of electricity in California? Thousands of people asked that question over the past, few days, weeks, whatever, kind of a simple query. That would be something answered at an inference data center. Now, the other type of data center is a learning data center, also known as an AI factory, is there to train, refine, and run artificial intelligence and machine learning models. So basically, it's like when you're coming up with a new model or you're teaching a new model, new tricks, it's training the brain. That's a learning AI data center. And in these data centers, the AI is basically analyzing, this is a learning center, billions and billions of data points simultaneously to figure out some patterns, to translate to different languages, or to generate content. So it's really doing a lot of things all at once. And that simultaneous processing has a big impact on the data center's usage of power. At the learning data centers, where you're kind of suddenly saying, hey, I need to calculate 1 billion points of data to answer this query or to figure out this new model, you get these tremendous power spikes. You may go from drawing a 1 megawatt of power for the data center, just kind of cruising along, to suddenly it might peak to 25 megawatts. It's a huge spike. Those huge spikes are things that the utilities don't really like. They can't like instantly run generators faster or find that power somewhere. So those learning AI data centers, they have big banks of batteries to kind of handle those spikes, because the only way you could deliver the power that all those servers need instantly is having a local source of power, and that's batteries. Now, but all data centers, even the inference data centers, have backup power, usually, once again, with batteries, because the batteries can deliver that power quickly. So very interesting that the data centers went in initially, hey, we're just going to use grid power. Then they realized, what if there's a blackout? What if there's a spike in power demand? They started putting in batteries. And then for the learning data centers, they said, hey, we need a lot of batteries, because only a battery can instantly deliver, I mean, within milliseconds, the extra power that all these servers are going to need. Now let's talk about the different sizes of data centers: small, medium, hyperscale data centers. I'm just going to kind of skip through some of the metrics, just kind of so you understand what we're talking about. A small data center, maybe 5,000 to 20,000 square feet. In terms of the rating, maybe 1 megawatt to 5 megawatts. It's still a lot of power, but it's not out of control. And the capacity, the number of servers are in there, and these are numbers from Google, so I haven't verified them, but it's pretty good range. They'd have maybe 500 to 2,000 servers in there. And this is something that would be a medium-sized business or enterprise or a regional telecom hub, or a regional data center. Then you've got a medium or a larger data center, and these may be 20,000 to 100,000 square feet. 100,000 square feet, we're talking about a pretty darn big building. And those are going to draw from maybe 5 megawatts to 50 megawatts, and they have capacity for 2,000 to 5,000 servers. I mean, just think about the servers. There's a rack, and that rack may have 20 or 30 servers in there. There's a ton of wire going in, and there's a tremendous amount of heat generated. So you're talking about a lot of servers. And this is where you may have standard co-location sites, regional cloud nodes, corporate headquarters that are using a lot of power. And then the last one, this is kind of really amazing, and this is kind of what's giving utilities fits to deliver the power, and then just they're writhing their hands together because of the greed, all the money they're going to make sending power. You've got these hyperscale data centers, and the hyperscalers are typically the biggest companies in the world, actually, certainly in the US, that are building big monster data centers so that they can run their business. Amazon Cloud Services, Microsoft Azure, Google's obviously there, Meta, Facebook, Oracle database company, Apple's also got systems this size. And these are enormous buildings. They could be 1 million square feet. I can't even imagine how big that is. They would have a power draw of over 100 megawatts. I've seen up to 1 gigawatt. I can't even conceive of that. I mean, a big power plant, I think about the Metcalf Energy power plant that's in South San Jose, that's 500 megawatts. It's not even 1 gigawatt. So you'd need basically 2 of those Metcalf power plants to power a hyperscale power plant. And then even then, you'd still need batteries. And the capacity, 10,000 to hundreds of thousands of servers. And these are the hyperscale data centers. They're going to, since they're so big, they're not going to be in a suburban area. They're way out there, remote. They're far away. It's being used to train AI. It's used for video streaming platforms where you've got tremendous amounts of data. And then global cloud services like Amazon and Microsoft Azure. So let's look at a map of data centers in the United States. This map is from NREL. It's fascinating to look at because you can see how the data centers are kind of sprinkled around the United States and where they're being built. Many of the data centers are in the Washington, D.C. area. I guess the government needs as much brain power as they can get. A lot of data centers along the Northeast and the Mid-Atlantic states and on the East Coast. And then we also see going out through the country, there's a lot of big data centers in Texas, and there's a lot of other data centers in the central U.S. What was surprising to me, there's not that many big data centers in California, even though that's where many of these, or the West Coast. This is where these companies are headquartered. What's also interesting is you look at where these data centers are, and then take a look at the red lines on this map. Those red lines are where you have really, really high voltage power lines. And they're connecting the biggest data centers. Why? Because those big data centers need a lot of power, and you're only going to get that with really, really high voltage power lines. And the other interesting thing, in addition to the red lines, is looking at the white lines. The white lines are the connections throughout the country where you've got high-speed fiber. So the data centers basically need power to run, and they need fiber to transmit the data to and from the data center. It's just absolutely interesting. We talked about this. This is the data centers are being rated by power. The big problem that the data centers is they need a lot of power. And where's that power going to come from? Comes from the utilities. That's for 100 years. That's how our country, that's how everybody around the world mostly historically has gotten power. They say, hey, to the utility, give me a wire, I'll run it. But in order to power these big data centers, even the medium and the small ones, 25 megawatts, 50 megawatts, certainly 100 megawatts, the data centers have to build new power plants because this is all new power demand. And as they build new power plants, they're going to need to build new transmission and distribution systems. So it's not that easy. They need to build the generation. Ideally, it would be with wind and solar because it's perfectly clean. The downside of wind and solar, as we talk about in a minute, is because the solar farm needs a lot of space and wind farms really don't work in a suburban area, they got to build them far away. From the power plant to the data center, you're going to need to build transmission lines. So those are those big towers with wires, or maybe you're going to do it underground, which is a fortune. And you're going to need to get specialized equipment like transformers and things like that. There's long delays for transmission lines, for transformers, for all that substation equipment. Bottom line, it's taking utilities 7 to 10 years to connect new data centers. So since these data centers are hearing from their friendly local utility, it's going to be 7 to 10 years before they basically connect them to the power grid. Utilities say, well, the heck with it. We can buy a natural gas turbine or 5 natural gas turbines, and we can run some natural gas lines, and we can have all the power we need in 2 years or less. It's amazing. So they're starting to build their own generation right on site. Now, we talked about this. The solar farm needs a lot of space. Wind turbines need a lot of space in a rural area. So there's not enough room where most of these data centers are being built for solar or wind. So most of these data centers are using natural gas turbines. They pump a lot of natural gas in. They're going to, hopefully burn it fairly clean, but there's still going to be a ton of CO2 emissions. And that's how they're solving the problem. Another way that they're meeting some of these needs is with a fuel cell. Bloom is a company that makes fuel cells. Fuel cells are basically the same as natural gas combustion. You're just basically taking the natural gas and you're breaking it down into carbon dioxide. And so you still get all those emissions. Some of these data centers are even using diesel generators because that's what they can get. The natural gas turbines, the diesel generators, even the Bloom fuel cells, they're incredibly polluting. So it's kind of ironic that many of the hyperscalers, like Google, like Amazon, like Microsoft, like Apple, they promise to reduce their emissions and they make commitments like we're going to be a clean, renewable, big company, and they don't want to create a lot of pollution. So they're basically making promises that they're going to be operating cleanly. The reality is they're going to have to break those promises. There's no way you can deliver clean electricity that data centers need without pollution with a natural gas turbine or a Bloom fuel cell. You're going to create CO2. There's almost no way around it. So the next question is, all right, well, if it's going to take a long time to connect with the utility, and if we connect with natural gas, it's going to be very polluting. How feasible is it to install solar at a new data center? Let's design the new data center so it needs solar. Hey, it makes a lot of sense. The problem is that the roof of the data centers don't have enough room for solar panels. The roof of data centers are already kind of cluttered with the cooling equipment they need to cool down the chips, the hardware, the AI processors. And then the second thing is the number of solar panels you would need, the sheer area that you would need is pretty tremendous. I did a kind of a back of the envelope calculation for a medium data center. Let's say it's a 25 megawatt data center. And let's say you're using solar panels that are on the average 12 watts a square foot. It's not the ideal, most efficient system, but they're pretty good. You need 50 acres of solar panels and in fields and fields outside this data center. So you kind of just imagine, data center and then a quarter mile all the way around or half a mile all the way around, you just have solar panels everywhere. Now, that would work. The problem is that you may not be able to get that much space. So in an urban area or a suburban area, you don't have enough land. You may find room for a building, but there's no way you're going to find 40 acres or 50 acres surrounding that building for all the solar that you're going to need. It's just not enough space. So it's a legitimate concern about all of the community, all of the ratepayers, all the homes and the businesses that are in the same location, city, state of a data center, it's a legitimate concern that they don't want their electric rates to go up because of all the new infrastructure that the utilities are going to be putting in to feed these data centers. And the way the utility business model works is they basically get to set the rates based on the construction they do, based on the infrastructure they put in. So if the utilities are putting in a power plant, a whole bunch of substations, and they're putting in long distance transmission lines, those are all very expensive. And the utilities get to raise rates to make sure that they can cover their costs with a guaranteed 10% profit on all those assets. So while the data centers are being built, the rates are going to be going up even before the data centers connect. And then the thing that people worry about to a very, very high degree is they say, well, what if the data center is only there for 5 years? Who's going to be around for the next 25 years to pay that data center off? Or what if they kind of change their mind and don't build a data center, but the utilities have already built the wires? This is what's happening. And it's good. The goal is to charge all the customers fairly, but if they try to charge the data centers fairly and then the data centers change their mind or they change their efficiency or they close down early or there's a new technology that comes out, the houses, the homes and the businesses in the area are going to be stuck with the bill. So the utilities want to say yes to data centers. They're basically saying, how are we going to do this? We're going to make a ton of money because all the extra assets, all the extra revenue that we're going to get, the consumers, the ratepayers are saying, hey, we don't want to pick up the bills. We don't want to get stuck with the bill for this data center that didn't get built. Or even if it did get built, the numbers didn't work out. And historically, what happens is the utilities have these things called stranded assets. Like, hey, we built all this extra capacity. It's called a stranded asset, and everybody else has to pay for it. This happens again and again in the utility industry, and that's what people are trying to avoid. There's obviously other issues about noise and pollution and traffic and things like that, but the biggest issue from an electricity ratepayer standpoint is they don't want to get stuck with the bill for this huge, humongous data center build out. And when you look at the expectations that the utilities are all making to build all the infrastructure, build all the power these days, the utilities are looking at $1 trillion worth of extra revenue. It's a huge number. Utilities are now merging together so they can figure out how to take advantage of this more effectively. It's going to be a really big problem. Having the utilities do this you can't put the solar in the area because you don't have enough room. Let's find another way. Well, the obvious other way, and this is something that I've been kicking around for better part of half a year, is why don't you install extra capacity that's needed on the local homes and businesses? It's a great idea. Now, here's the problem. Although you can, and the power could be generated on a collection of residential and commercial rooftops, parking lots, government buildings, things like that, utilities want to build the power plants. And when the utilities see that somebody's going to put solar and batteries in without their revenue generating from that, they push back on it. So utilities don't want competition. They're unfortunately, utilities are very poorly regulated. In fact, through all the financial contributions that utilities make, and I see this happen in California, it's just maddening because people say, why do our electric rates keep going up? And why does our government not stop it? It's because of so many financial contributions being made by the utilities to our government, to the regulators. And they've basically, and this is a concept called regulatory capture. So the utilities who are supposed to be regulated by the Public Utilities Commission, they've captured the Utility Commission, and they're basically able to control the decisions. So it happens again and again. It's happening to rooftop solar, commercial solar, everything else, everything that's not utility solar. The utilities effectively deny the local build out of rooftop solar and storage. And it's a big problem. It's one of the reasons why net metering changed, one of the reasons why your economics for solar aren't as good as they were 5 years ago. Got the background. We all kind of understand a little bit better the terminology related to data centers. We understand the opportunity and the number of data centers that have to go in. We understand the resistance that utilities have to competitive sources of power. I kind of look at it, I step back and I say, you know what? There's 4 outcomes that will happen based on the rush for data centers to be constructed, based on the utilities trying to provide that power, and based on the reactions, the NIMBYism, not in my backyard, the opposition that's developing throughout the country against data centers. One outcome is that the utilities are going to build those power plants, as needed by the data centers are going to go up everywhere, and more power is good. But the rates for everyone are going to go up. It's almost inevitable. It's baked into the utility business model. No matter what they say, that's what's going to happen. The second outcome is the data centers are going to say, well, we can't get the power from the utilities because the utilities don't want to do it because they don't want to raise everybody's rates, or they've been told they can't raise everybody's rates. Data centers are just going to put in their own natural gas power plants. The demand for natural gas generating systems has gone through the roof. There's now like delays of 3 or 4 or 5 years just to get high quality natural gas turbines that take the natural gas, spin the wheel, and generate power. So what's going to happen is the data centers, and they're already doing this, they're going to put in their own natural gas power plants. That's going to create tremendous pollution. And the data centers may say, oh, we're going to use carbon capture and sequestration. Between you and me, and candidly about this, carbon capture and sequestration on this scale is a bunch of BS. There's no way they're going to capture that carbon dioxide efficiently. There's no way they're going to be able to permanently sequester that. There's no use we have in the world for all that carbon dioxide. We can't make that much more soda. All right, so that's the second option. The data centers are going to put in their own power plants, and it's almost always going to be natural gas. And we talked about it. It doesn't make a lot of sense for them to put in solar. They may put in a few solar panels on the parking lot, but they just don't have the 40 or 50 acres they need of solar that they'd like to put in. The third option is the communities, the local governments are going to just say, no, you can't build the data center. And the data centers are going to freak out, and they're going to have to cancel their plans, or they're going to have to find a way to convince the locals that it's actually going to be okay. But that's not going to be easy. And locals are pretty smart. They just can't be patted on the back and say, don't worry, your rates won't going up. Not a lot of trust with utilities. And then the fourth option is communities and local governments and states are going to require the data centers to install some kind of local storage and solar. And that's practical. There's a way to do it. There's plenty of rooftops in commercial buildings on which that solar can be installed. Plenty of space for the batteries that are going to be needed. So that's going to make sense for the data centers. It's going to make the community more comfortable. Gee, I mean, if you can say to the community, we're going to put in all these commercial and parking lot solar plants, and if you have a sunny roof, we're even going to help put the solar on your roof. The community's going to love that. But who loses? The utilities' profits are going to go down. So they're going to push back on that option 4 as hard as they can. I'm hoping that option 4 works out. I don't want to see a halt of data center rollouts. I don't want to see data centers put in their own natural gas plants. The electric rates are going up for everyone, but I would expect that we're going to end up with somewhere between item 1, rates are going to go up, and the item 4 is that the data centers are going to figure out a way to make a deal with the utilities so that they can install local rooftop solar and storage. All right, so just wrapping up, obviously, installing rooftop solar and storage in the area around data centers makes the most economic sense for ratepayers, and it makes the most economic sense for data centers because it's the cheapest way and the fastest way to deliver the power. And you just got to remember, you got to keep in mind, the utilities will not be able to generate as many profits. So that's why you're going to see them fight tooth and claw to maintain their monopoly and maximize their profits, basically to the detriment of their customers. All right, that's all the time we have on this week's Energy Show. Thanks to all of our listeners for tuning in. And if you missed any of today's show, you can always go to our website at energyshow.biz and listen to the podcast.
Thanks for tuning in to this week's Energy Show.